Okay. We have these questions. B is vector AI minus C. First thing we want to do is find V cubed. Okay. That's a complex number. Okay. It's written with an arrow over it because your book bold faces it. Okay. Which means your book is kind of using vector notation. You don't necessarily have to put arrows over these, but using the V, W, and so forth, and U, it just naturally invokes the vector terminology, okay, in the vector images. So if V is 3i minus 9, for example, depending on your numbers, then the negative 9 is the real part, 3 is your imaginary part, and you can visualize this as a vector, okay, with some angle theta. Okay, well, theta is the inverse tangent of three over negative 9 plus okay. We generally do mathematics in radians. So it's the inverse tangent of 1/3, negative 1/3, and that would be the negative inverse tangent of 1/3 plus pi. So it is 3 square root of 10, okay, times the sine of theta plus I sine theta. So V cubed will triple your angle. Now, there's no easy way to triple the inverse tangent of 1/3 plus pi. Okay, but it's going to be coterminal with an angle. Well, if this is theta, you know, it's this much shy of pi, or 180 degrees. If you were to think about it, if you went another 180 degrees, you'd end up here, but you end up a little bit short of that. So V squared. And the magnitude of V is pretty big, but V squared is going to be here, and the tip is going to be off of them. It's going to be much longer. Okay, and then you come back here, and you come to an angle about here, and your V cubed will be along this line. And again, further out. Okay, square root of 90 is just slightly less than 10. So magnitude of V squared will be somewhat less than 100. Okay. And V cubed will be somewhat less than 1,000. I'm guessing mid to high 800s. Okay. So it's going to be too long to draw on this picture, but we need to understand this demography. Okay. And of course, it can be verified. V squared is going to be this. It's called the polar form of the complex number. Something that is a pretty standard topic in pre-calculus. Matter of fact, we're working on assessment of pre-calculus. I'm working like crazy on assessment of pre-calculus. There's been some debate about how we do polar form. different instructors who want to see polar form. You have the RE to the I theta form. Okay, well, regardless, there's your magnitude. Well, there's your V squared. Now you could square V using the distributive law, right? I don't want to cube it. Now you could cube it using the binomial theorem, which I hope you know. Okay, it's kind of important. And we square this, we're going to get 9I squared plus 81. And then we're going to get minus 54I, I believe, which is then 81 minus 9, which is 72, minus 54I. Okay. Well, you go out 72 units this way and down 54 units this way. This is very plausible because it's, well, it's just plausible. Okay. Also, the angle of this thing, the magnitude of V squared, is the square root of (72) squared plus 54 squared. Okay. Note that these are both multiples of 9, 72 and 54. That's like 6 times 9 and, or sorry, 8 times 9 and 6 times 9. Okay. So you got 8 squared plus 6 squared times 9 squared. Okay, in here. Well, 8 squared plus 6 squared is 100. So you got 100 times 9 squared. Okay. Now you can work that out, which is easy to do with the numbers, but if you factor these things, you see what happens. You see that you're going to get 3 square root of 10. Okay. And also, since the square root of 90, well, you square the square root of 90, you get something pretty close to 100. Right? But if you got a triangle 72 this way and 54 this way, very plausible if that's about 100 on the hypotenuse. You want to be able to visualize this, not just run them out visualizing, because it gives you more power in solving problems. And I want to get the visual idea of complex numbers. Okay, well, now, V multiplied by V bar equals what? Well, that's 3I minus 9 times negative 3I minus 9. And that's negative 9 I squared plus 81. And then we have a negative, well, we have a positive 27I. I'll write it out, 27I, and a negative 27I. That's 90. You can work out the arithmetic of the details. It's just the magnitude, the square of the magnitude of V. Okay. And of course, this is one of the things you have learned, V times V bar equals square of the length of V. Represented in this form. Okay, so that's pretty easy. Now let's go to this, because this gets into something we need to talk about for a bit. Okay. Now we got the equation. And let's say we've got 7I minus 9, why not? Okay. What do we get? Well, that's going to be C1 times 3i minus 9 plus C2 times negative 3i minus 9 equals 7i minus 9. Which tells us then that group it like this: 3C1 minus 3C2 I plus negative 9C1 minus 9C2 equals 7i minus 9. So that this should be kind of familiar. The only difference is that I'm grouping my coefficients of I and my real coefficients, so I can set the coefficients of I here equal to 7, and the real coefficients equal to negative 9. So we get the simultaneous equations. 3C1 minus 3C2 equals 7. Sorry, negative 9. No, 7. Go blind. Then negative 9, C1 minus 9, C2 equals negative 9. So we can easily solve for C1 and C2. Let's see. Yeah, I don't want to solve that in my head, but that's straightforward to solve. Now, no matter what complex number I put over here, I'm going to be able to solve these equations. Okay. I'll put any two numbers over here. In particular, if I put zeros over here, I'll be able to solve for C1 and C2. Okay, so let's look at the equation. C1 V1 plus C2 V2 equals 0. Then 3C1 minus 3C2 equals 0. Negative 9C1 minus 9C2 equals 0. Okay. This tells you that C1 equals C2, this equation, right? This equation tells you that C1 equals negative C2. Okay. There's only one solution. What solution is there to this equation? What's the value of C1? Can you show me with your fingers, your hands? 0. Okay. And the value of C2, 0. Because this is a contradiction of C1 and C2 or anything but 0. The only number that can be, the only two numbers that can be equal and also equal and opposite, that's 0. Well, this proves that we can always solve this. Because this shows that these two vectors are linearly independent, or these two numbers can be regarded as linearly independent vectors. And if you put them, if you plot them, so here's 3i minus 9. And where is negative 3i minus 9? Complex conjugate. Negative 3i minus 9. Well, negative 3i minus 9 is going to be down here, right? In the complex plane, these things aren't parallel. So they form a basis for the complex numbers. Okay. Okay, well, that's going to be important here. I didn't quite say that right, but I'll leave it for a moment. Okay. I'm looking at the problems that I'm going to assign. I just want to make sure that I get the notation. Okay, let me pause a minute. And let me also zoom in because it's zoomed itself back. Got to see too much of me and too little of the board. Okay, so R2 consists of ordered pairs of real numbers. C2 consists of ordered pairs of complex numbers. In C2, constants are complex numbers. In R2, of course, your constants are real numbers. Okay, so just going to pose a question. Is this a basis for C2? Well, fine, whether. A set is a basis. First, you set test for linear independence, right? How do we test for linear independence? You test whether C1 V1 plus C2 V2 is 0. What do you mean by C1 C2 plus C1 V1 plus C2 V2? test with it. This gives you the zero vector, which would be 0, 0. So you get okay, get this. Now you simplify this into real. Look, I wrote this out again. That's not right. And what you get is C1. Well, this is 2C1 minus C1 I plus C2 minus 2C2 I, comma, 2 C2 plus C2 I, and that should be 0, 0. What I wrote down there, some kind of disorientation going on there, but anyway, there we have it. So that we add the first components, we get 2C1 plus C2 minus 2C2I, negative C1I plus C1 plus C2I should equal 0, 0. And this gives us two equations at C1 and C2. Equations are 2C1, well, two C1 plus C2 minus 2C1I has to equal 0. And C1 plus, we'll do C2 minus C1 I equals 0. Now this is 0. I didn't write it in complex form, but 0 in the complex plane means 0 plus 0I. So I can certainly write 0 plus 0I. And now I can see that C2 is going to have to be 0 because negative 2C2I has to be 0. Okay? And C1 has to be 0 because that's a real part of this imaginary number, and that real part has to be 0. Now, does that make sense? Might be a little shaky because the difficulty you've got to kind of overcome is these are all complex numbers. Okay? If these weren't complex numbers, if it was this plus this and this equals 0, and this plus this equals 0, without the I in there, you'd have a solution. But that's not the situation. You're in a complex plane, so these, again, these zeros over here are complex zeros. Okay. Now this defies any kind of graphing because each component of each of these complex numbers is itself a complex number, which should be represented in two-dimensional form like we did previously, okay? So you've got two components, each component being two-dimensional. So this would have to be represented in four-dimensional space, and we can't really visualize that. So you want to kind of get used to that idea. Okay, well, that's not a complete answer, but you see plenty of examples, and that's, I proved that these are linearly independent, okay? In your book, you see simple proof that C2 is of dimension 2. I don't want to take the time to write that out because I want to look at some different things, but okay. Cn is of dimension n. So the first problems you're going to see simply ask you, is this set of bases for Cn, okay? Sometimes it's two vectors in two-dimensional space. Sometimes it would be three ordered pairs, which means you'd be in C3, okay? I think there's even some, I don't know if I assigned it, in C4. All you have to do is test for linear independence. Once you know that Cn is of dimension n, you know you need n vectors in your basis. So for example, I'm shortening these to two-dimensional vectors because I'm running out of space, not because that's a valid thing to do. Okay, so we can do this. And okay, what complex space do these numbers live in? They live in C3 because they have three components. So it's C3 because each ordered triple consists of three complex numbers. All right, so let me just ask you to do something. Just write the equations you would solve to take a step simplifying the equations. Test this. In other words, just do what I did, but remember you're in R3, and that's going to change things a little bit. But all you're doing is using the familiar test for linear independence. This plus this, the linear combination is 0 if and only if all your constants are 0. Okay, good. Okay, so people follow the procedure. Now, I'm not going to write all this out because everybody pretty much wrote it out correctly. But it's analogous to this, and when you get down to the end, well, you're going to have three equations that look something like this, right? Except they're each going to have a C1, a C2, and a C3, unless something cancels out, okay? And that's going to give you ultimately 6 equations. Now you can see that this equation, the system of equations is equivalent to the augmented matrix 2, 1, 0, -2, 1, 0, -1, 1. Zeros over here. Now, of course, this equation here tells you that C1 is 0. This tells you C2 is 0. No free variables. You could row reduce it if you wished. And the easiest way to row reduce it is to bring this one up to the top, put this one in the second position, and then divide this one by -2. So you get a 1, 0, 0, 1 up here, and then those ones will wipe out everything below them. Okay. So these two equations would end up getting wiped out. Whether you see that or not, it's good for you to actually write that out and take that back to the whole idea of simultaneous equations, augmented matrices, and so forth, so that you really understand how this test works. Okay. And you're going to have tests. You know, that half the problems. Okay, there are 2 columns of problems. First column, almost everything in that column is basically this, except something that's really easy. So I'm going to show you the one thing that's really easy. Okay. Fix this. Okay. And let me back up a minute. I'm not sure that's exactly how the book presents it. Okay. I think I did this before I defined the dot product. Okay. So it's actually not a dot product. It kind of works, but let's say okay, there's your expression in for a complex vector with 2 components. Okay. And I want to be sure. And that defines your dot product. So that's really. That's the definition of U dot V. So we're going to get into that. Okay. Somehow, seems like they ask you this before they talk about their products. And also, I say the distance. This is the Euclidean distance. And they do define the Euclidean dot product. okay? And it's just this. In general, an inner product has the property that the inner product of two vectors and I think I'm writing that down wrong. And we'll talk about why this is. Try to put my bar in the wrong place. Okay. We have this, okay? There's a reason for this, but then there are other, and we've talked about it a little bit. There are a couple of other properties just with constants, like if you do U times KV, it's the same as KU dot V. Okay, stuff like that. So that's pretty trivial to verify. But the big one is that U dot U is zero if and only if U is the zero vector. And this is what we're saying. And also U dot U is always greater than or equal to zero. Now, the reason we do the conjugate up here is because if we didn't, if, for example, write this out differently. Okay, we just have, okay. If U is just the one-dimensional vector A plus BI, I'm sorry. No, that doesn't make sense. Okay, let's say we got a two-dimensional vector. A, B, I. Dot A, B, I, okay? If that was this wouldn't work as an inner product because this is A squared minus B squared. Okay. And that's really what this comes down to. Your inner product, you don't want it to be negative. Because, for example, we want to use inner product to represent distance. We don't know what we have to worry about a distance is positive or negative. Distance is not positive. Distance is never negative. Displacement can be positive, distance can't be. Okay, well, just by this example, you can see that this definition isn't going to work. Okay, so if you had like U, dot U equals this. Clearly, this could be negative. It's like a dot product of the conjugate. And I'm messing up notation here, but there's your idea. And this would be A squared plus B squared. Now I should have, instead of writing a dot product, I should have written the general inner product as U comma U, U comma U, which is a notation you're interested in. I mean, you're used to, okay? So the inner product of U with U couldn't be this. It certainly can be this. And this is like U dotted with U bar, the complex conjugate. So this would be your Euclidean inner product. General inner product you would use for example. The inner product QV has to be the conjugate of the inner product VU. Remember that U and V could be 2, 3, 4, 5, 6. Each of these could be some number of complex numbers, okay? Could be an ordered multiple, an ordered pair, an ordered triple, an ordered fourple, okay? And then the others expressed the same. And then you have questions in the homework. They ask you, they give you a formula. Okay. Product and ask to verify whether the thing is in their product. Okay. Usually the thing that you want to go straight to is this, because that's going to tend to be contradicted. Okay. And if this isn't contradicted, then you test this. Okay. And the other stuff, well, you don't get anything conclusive, you test the other stuff. Okay. Let me make sure I don't duplicate. You've got a transformation that takes the vector I, 2 minus I, to the vector 1, 0. And this vector to this vector. Could be any pair of vectors. Okay, well, then the matrix A multiplied by I, 2 minus I, should equal 1, 0, right? This means that you're going to have to find number here and a number here. Make this 1, okay? And numbers here that make this 0, okay? What two numbers here can give you 1? Well, you gotta think about it a little bit. Usually the numbers are going to be a little easier than this. For example, if you have 1, 1 here, then you get I plus 2 minus I would be 2. And this tells me that I should use 1/2, 1/2. That's going to give me 1 in this way. Down here, I've got to have 2 numbers such that when I do this, I get 0. And that's going to be a little tricky. Okay. So don't worry too much about this example, but you'll see other examples. And the ones in your book are pretty straightforward. Okay. Okay. There's a little bit about image and pre-image and stuff like that. A whole lot like what you're saying. If you don't get those, we'll talk about it next time. Okay, so where we are, Thursday we'll talk about section 8.5. You probably want to review what you know about symmetric matrices. Okay. Like they have real eigenvalues, they have a complete set of eigenvalues, orthonormalized. You can do an orthonormal eigenalization and all that stuff. So you kind of want to refresh yourself on that because the same kind of stuff happens with complex matrices. Okay, just a little more complicated. So deal with these complications. Of course, that'll be your last. I won't say necessarily be your last assignment. There's one more thing I want to do, but that's kind of the end of chapter 8. Then we want to talk a little bit more about stochastic matrices and how eigenvalues work in with stochastic matrices. Okay.